Okay, let's be totally honest here. If I asked you right now, this very second, to calculate 1.04 to the power of 20 without grabbing your smartphone or a calculator, could you do it? For most of us, that looks like an impossible mountain of manual multiplication. But what if I told you there's a mathematical superpower that can turn that nightmare exponent into a super simple, basic addition problem? Well, today we're unlocking that exact superpower.
Welcome to today's Explainer. We're going to completely demystify some of the absolute most powerful tools in math. We're talking about logarithms and their magical counterparts, anti-logarithms. We're going to break down how to use them, why they actually work, and how they quietly run the calculations that dictate our daily lives, from your bank account all the way to the population of the planet.
All right, here is our game plan for today. First up, the reverse of a log, the anti-log. Second, how to actually read an anti-log table. Third, we'll tackle the anti-log of negative numbers. After that, real-world applications. And finally, we'll look at population and depreciation.
Okay, let's jump right into Section 1, reverse of log, anti-log. So let's start with the absolute basics. You know, in math, pretty much every operation has a reverse, right? Addition has subtraction, multiplication has division, so it's really only fair that logarithms have an opposite too. Enter the anti-logarithm. It is exactly what it sounds like, just the absolute reverse function of a log. Think about it like this. If the log of 100 to the base 10 is 2, well, to reverse that, the anti-log of 2 is simply 100. It's literally a mathematical undo button.
I actually love this analogy because it brilliantly illustrates the dynamic between the two. Think of a logarithm as a kind of, math fever that you give an equation to break it down and make a massive calculation manageable. But obviously, you can't just leave your numbers sick with a fever. Once you've solved the easy math, you have to administer the anti-log. It's the antibiotic. It cures the equation and brings your number right back to its normal state.
Moving right along to Section 2, how to read an anti-log table.
So how do we actually find that cure in practice? Well, when you're calculating manually, you aren't using a calculator, you use an anti-log table. But there is one golden rule you've got to remember. Anti-log tables only ever deal with the positive fractional part of your number. We call that the mantissa. Now, what's really interesting here is just the structure itself. When you flip to the back of your textbook, the table looks huge and intimidating, but it's really just 3 simple sections. On the far left, you've got a column starting from 0.00, going all the way down to 0.99. Right next to that is a block of 10 columns labeled 0 through 9. And then finally, on the far right, there's a smaller section called the mean difference, covering 1 through 9. And that's it. That is your entire toolkit.
So the crucial point is how we actually navigate this thing. Let's say you need the anti-log of 2.1647. First, you completely ignore the 2 for a second. You just take that positive decimal part, the 0.1647. You go down the left column to find 0.16, and then you slide across to column 4. You note that number down. Then you slide even further right into the mean difference column for 7, and you add that tiny little value to your number. For 0.1647, this brings you to the digits 1461. Finally, you look back at that original 2, your characteristic. You just add 1 to it, which gets you 3. And that 3 tells you to place your decimal point exactly 3 spots in, giving you 146.1. Boom, you've literally just read an anti-log table.
All right, Section 3, anti-log of negative numbers. Let's see what happens when we introduce a bit of a twist. What happens when your logarithm actually gives you a negative number? Well, as we just learned, the anti-log table strictly refuses to work with negative decimals. So if you have a standard negative number, like negative 1.2357, you are, mathematically speaking, completely stuck. The whole number is negative, including that 0.2357 decimal part, and our table simply won't accept it. But to fix this, mathematicians use a very clever workaround called bar notation. Look at the second item here, 2 bar 0.7643. This genius little trick means that only the integer, the 2, is negative, while the decimal part, the 0.7643, is wonderfully perfectly positive. So how exactly do we get there? We perform a little bit of mathematical surgery. You take your negative number, negative 1.2357. You look at the integer, which is negative 1. Then you take the very next integer up, which is 2. Now you simultaneously add 2 and subtract 2 from your value. That negative 2 gets pushed all the way to the front and becomes your bar 2. Then you mathematically combine the plus 2 with your negative 1.2357, and the result? A perfectly positive 0.7643. You stitch them back together to get 2 bar 0.7643. Now your mantissa is positive, and you are officially ready to look it up in the anti-log table.
Seriously, it's such an incredibly elegant workaround.
Which brings us to Section 4, Real-Life Applications.
Now, you might be sitting there thinking, okay, this is great theory, but when am I literally ever going to use this? Well, the truth is, while your smartphone hides all the heavy lifting from you today, logarithms are basically the invisible engine running the modern world. They definitely aren't just for textbook exams. We're talking compound interest in your bank account, tracking massive global population surges, measuring the half-life of radioactive materials, figuring out the exact depreciation of your car, your monthly EMIs, and even measuring the devastating power of earthquakes on the Richter scale. Honestly, they are absolutely everywhere.
And that leads right into our final part, Section 5, Population and Depreciation. Let's actually put this superpower into practice on some massive real-world problems. Remember that terrifying calculation from the very beginning of this explainer? 1.04 to the power of 20? Well, here is exactly where it comes from. Imagine you invest 10,000 rupees for 10 years at an 8% interest rate, compounded half-yearly. Now, because it's half-yearly, your rate halves to 4% and your time periods double to 20. So suddenly you have to calculate $10,000 multiplied by 1.04 to the power of 20. But by taking the logarithm of both sides, that terrifying exponent of 20 just drops right down and becomes a super simple multiplication problem. So once we find the log of 1.04 in our table, we multiply it by 20, and then, remember the antibiotic, we cure the equation with our antilog. Doing that, we find our total amount is $21,880. Subtract our initial 10 grand, and we get our exact compound interest, $11,880. What looked like an impossible mountain took just a few simple table lookups. Crazy, right?
All right, let's scale things way up to the entire human race. Scientists use a formula where population equals 4.7 times 1.02 to the power of t, where t represents time since the year 2010. So, if the global population in 2020 was roughly 5.72 billion, in what exact year will it completely double to 11.45 billion? Once again, we are hunting for a pesky exponent. By setting the equation to 11.45 billion, throwing logs at both sides to bring that t down to the ground, and dividing out the numbers, the math reveals that t equals 45. And since our baseline year in the formula was 2010, we simply add 45 to it. The math predicts the global population will perfectly double by the year 2055. For sure, a massive number to think about. Finally, let's talk about things actually losing value. Imagine buying a brand new Activa scooter, only to see its value totally plummet the second the shiny new 7G model hits the streets. That is depreciation. Now let's scale that up. Imagine a heavy industrial machine bought for 800,000 rupees. It depreciates at 7% every single year for 10 years. Because the value is dropping, we subtract that 7% from 100%, leaving us with 93% of the value each year. Plug that into our formula, and we get 0.93 to the power of 10.
Now, taking the log of 0.93 actually gives us a negative characteristic, which means, yep, we get to use our awesome bar notation trick to keep the decimal positive. After multiplying by 10 and taking the antilog, we discover the machine is now worth just over 384,000 rupees. Think about that. In 10 years, more than half of its value has completely evaporated.
So, from avoiding massive manual calculations to predicting the future of our global population and tracking the value of our investments, logs and antilogs are an absolute superpower. You've now seen exactly how to decode the tables and cure the math fever, but honestly, it leaves me wondering, if these invisible calculations are powering everything from the interest in your savings account to measuring the actual tremors beneath your feet, what else in your daily life is quietly being run by complex math that you haven't even noticed yet? Definitely something to think about. Thanks for joining me on this explainer, and keep questioning the math behind your world.